This is the amateur radio general license training. If you are taking a different flight, please exit the airplane and get on a different flight. We're going to be talking about, I'm going to be talking about section G4, which is amateur radio practices, which covers a total scattershot across the manual. So there's stuff from a variety of different chapters. I've tried to organize it into kind of the flow that the book uses so that if you want to go look stuff up, you're looking stuff up in the right chapters. So that would help if I'm in the right window. By the way, I'm Peter, KN6UAW. Have been licensed for about 2.5 years now. Got my extra a few months ago. The general license exam looks really trivial next to the extra, so for all of you taking the general, it's not that bad. You only have to read the book a couple of times. All right, so this section has 60 questions. It's broken up into 5 sections, including station configuration and operation, tests and test equipment, interference, grounding and bonding, speech processing, operating near the band edges, and then mobile and portable HF stations. There are 5 exams out of these 60 questions. I'm sorry, 5 exam questions out of the 60. So a lot of material to cover, some very interesting stuff to think about and to learn about, and it firmly gets you grounded into HF operations, which is actually quite a bit of fun. So I've organized this leveraging the book into alternative power, basic test equipment, etc. I don't need to read all of this to you. We'll see it as we go through the presentation. If there are questions, please put them in the chat so that I can notice them, because that's all I'm really seeing right now other than the presentation. All right, so alternative power. Each of these sections will reference the area in the manual where the information is coming from and where the questions are generally answered. For this section, essentially they're talking about solar power and how solar panels work. And a solar panel is really a silicon PN junction. When the sun shines on it, electrons flow, creating a DC current. When there is no sun shining on it, you want to be sure, if you have batteries attached, you want to be sure you have a charge controller in the middle, because you want to make sure that the current is always flowing from the solar panels into the batteries and not from the batteries back into the solar panels. Given this community, most of us are already familiar with solar, so I'm not going to spend a lot of time digging into the details here. There are a few questions in the exam possible. First one, in what configuration are the individual cells in a solar panel connected together? And they are actually wired together within the panel in a series parallel configuration to bring the voltage up and to bring the current up. What is the approximate open circuit voltage from a fully illuminated silicon photovoltaic cell? Yes, you too can learn to talk. It's a 1/2 volt, which is pretty typical for a silicon PN junction. So as you think about silicon PN and other areas of the exam, think about it here as well as being about a 1/2 volt. So why should a series diode be connected between the solar panel and a storage battery that is being charged by the panel? We touched on that briefly. You want to ensure that there is no battery discharge through the panel when there is no or very little solar illumination on the panel. So basically, it keeps the current from flowing from the battery back into the panel. And the last question in this section, what precautions should be taken when connecting a solar panel to a lithium iron phosphate battery? You need to have a charge controller. And generally, you should always have a charge controller, but this question is specific about lithium-ion batteries. So pretty basic stuff about solar. Moving on, so let's talk about test equipment. Some of this gets covered to some extent in the technician exam. It gets deeper here in the general exam. The general pieces of equipment that are going to be tested against are voltmeters, multimeters, digital meters, which are measuring current, resistance, and voltage. Oscilloscopes, which are probably, I think, new in the general topic area. And an oscilloscope is basically a display that allows you to look at a signal. So it is measuring, it's displaying voltage on the vertical scale. So it's going up and down for voltage as the voltage goes up, and the horizontal scale is time. So as the voltage changes over time, you see what the signal looks like. Classic oscilloscope picture has a sine wave in it, which is just a nice, clean little single frequency signal. When we're dealing with RF, we're generally not dealing with that kind of clean signal. We have a lot of other stuff going on. So scopes are a great way to be looking at RF signals. An antenna analyzer, a great tool to have in your toolkit if you're putting up your own antenna or building your own antennas. Very versatile. You can measure the standing wave ratio. So how close to perfect one-to-one SWR are you going to get with your antenna at any particular frequency? You can measure the antenna and feed line impedance. You can measure velocity factor, which is essentially the degradation from the speed of light that the electrons travel down the coax or the ladder wire. You can measure the electrical length and then the characteristic impedance of the feed line as well. And then the last item is a directional watt meter, which is basically a very simple antenna analyzer because a watt meter is looking at forward and reflected power. Standing wave ratio is the ratio of forward to reflected power. So good tools to have in your toolkit. Probably, in my opinion, the two most important would be a multimeter and an antenna analyzer. The scope is handy at times, but it's not something you're going to probably use every day unless you're building equipment or you're operating with some of the older tube-based equipment where you need to put a scope on it to see how it's performing. All right, so the questions in the exam. What item of test equipment contains horizontal and vertical channel amplifiers? That will be the oscilloscope. It's the only piece of test equipment here that has two data inputs, or two signal inputs, if you will. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? You can measure very complex multi-frequency waveforms. You can see them on the screen. You can do filtering with an oscilloscope to filter out things that you're interested in. Again, great piece of test equipment. That's the one you want to use if you're looking at complex waveforms. Which of the following is the best instrument to use for checking the keying waveform in a CW transmitter? The key part of this question is waveform. And so again, you want to pull an oscilloscope out to look at that waveform when your CW signal is changing from high to low. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? Well, you want to see what the RF is doing, so you want to see what the output voltage of the transmitter is. So you're looking at the attenuated RF output of a transmitter. Attenuated, so the question is, the answer is what the answer is, but from an operational perspective, don't put 100 watts or 1500 watts into an oscilloscope. You'll have a piece of melted metal next to your bench next time. So you do want to use an attenuated signal, not a full power signal. Why do voltmeters have high impedance? It's in order to decrease the loading on the circuit being measured. So you want to be able to put the voltmeter into a circuit and not have it affect the operation of that circuit, but just have it measure it. So very high impedance in order to decrease the loading. What is the advantage of a digital multimeter as compared to an analog multimeter? Okay, so in a digital multimeter, you've got a digital display. You're seeing numbers. You're not seeing a needle move back and forth across the display. So, the digital multimeter can give you a very high precision measurement, 12 12.297 volts, for example. Whereas if you're looking at an analog voltmeter, you may see that it's 12.7 something, but you don't know exactly what it is. When is an analog multimeter preferred to a digital multimeter? And this is particularly useful when you're adjusting circuits for maximum or minimum values, because you can see the needle move sometimes more quickly than you'll see the digital display change. And the needle will give you a faster indication of what's going on. Which of the following can be determined with a directional wattmeter? Well, remember that a directional wattmeter measures the forward and reverse power, and that is how we calculate standing wave ratio. So the correct answer for this is standing wave ratio, SWR, as we typically call it. Which of the following must be connected to an antenna analyzer when it is being used for standing wave ratio measurements? Well, you want the antenna analyzer to analyze the antenna. Then the antenna system is really the antenna, any chokes that might be on the line, and the feed line. So you put it at the feed line where you would normally hook your feed line up to your transmitter or to your antenna switch. What effect can strong signals from nearby transmitters have on an antenna analyzer? Well, the antenna analyzer is looking at the signals. Well, let me back up. So an antenna analyzer essentially puts a very low power signal out onto the feed line, out to the antenna to measure the forward and reflected signals. If there's a strong signal coming in on the antenna, that's going to overwhelm the analyzer, and you're going to get an interference situation with the SWR readings. Which of the following can be measured with an antenna analyzer? Editorial note, lots of these questions are basically the same questions, just phrased in different ways. So if you understand the answer to one of these questions, there may be three other questions that just vary the phrasing. Only one of those is going to show up on the exam. So which of the following can be measured with an antenna analyzer? You can measure the impedance of the feed line, the coaxial cable in this example. So very helpful sometimes, particularly if you think there's a problem with your feed line. You can put an antenna analyzer on it and see if the feed line looks okay from the analyzer's perspective. Okay, so let's talk about transmitters. With respect to this section of the exam, there's lots of other transmitter content on the exam, but we're circling in on the G4 section. So HF transmission modes include CW, SSB, known as single sideband, AM, FM, and then many, many digital modes, of which FT4, FT8, and RIDI are examples. The FCC states specifically that phone signals should not occupy more bandwidth that is dictated by good amateur practice. So there's not a specific bandwidth number stated by the FCC in the Section 97 rules. It's really what is good amateur practice, and that has been decreed to be essentially a signal that's 3 kilohertz or less for SSB and 6 kilohertz or less for AM. And then there's questions about overmodulation. So what is overmodulation? It's essentially that you're overdriving the transmitter with an excessive signal amplitude. And so you're generating signals that end up going beyond the typical 3 kilohertz bandwidth for SSB or 6 kilohertz bandwidth for AM or more for FM, although FM isn't used as much on the HF as it is on VHF. Transmitter's automatic level control is used to reduce the output during voice peaks, and that helps to reduce or eliminate overmodulation. And that's typically done automatically, and it's typically either turned on or off Some transmitters will give you the ability to adjust the ALC level, and some it's more just binary on or off. There's a measurement for transmitters, which I think is kind of historically used more with tube amplifiers than the transistor or solid state transmitters. It's called two-tone test. And so essentially there's two non-harmonically related signals, tones at 700 hertz and 1900 hertz injected into the transmitter, while you put the transmit output attenuated on an oscilloscope, and you can see what's happening with those signals. And you want to see two clear tones versus seeing variability or distortion in the output signals. When transmitting, you need to stay inside your band. So if you're in the 20-meter band, you need to make sure that if you're transmitting upper sideband, that you're staying under the top of the band, and if you're transmitting lower sideband, that you're staying over the bottom of the band. So since we're talking about single sideband, either upper or lower, we want to make sure for lower sideband, you're 3 kilohertz above the bottom, and for upper sideband, you want to be 3 kilohertz below the top. And this is the setting on your transmitter. So the transmitter VFO will typically show the carrier frequency that you're transmitting at, and your LSB will be below that, and your upper sideband will be above that. One other topic here, speech processing for amplitude modulated signals and single sideband signals effectively increases the average power of the overall signal by compressing the audio peaks. So it takes the peaks out of it, which enables let's say you're transmitting at 100 watts, that 100 watts has basically been squeezed into a smaller bucket so that you get more power within that bucket and you're not wasting a lot of power outside of that bucket. If you overprocess the speech, you can end up with a very distorted and unintelligible signal. So you do want to be careful about how much speech processing you set on your transmitter. So let's go through the questions that are related to transmitters. Why should the ALC system be inactive when transmitting audio frequency shift keying data signals? Since the ALC has the ability to essentially distort the signal, you don't want that distortion on AFSK. So you basically want to make the ALC off, turn the ALC off when you're doing AFSK. Essentially, when you're doing any digital, you want your ALC system to be inactive. What signals are used to conduct a two-tone test? We just talked about that. That's two non-harmonically related audio signals. The traditions are 700 and 1900 hertz. You can do whatever you want. You just want to make sure that they're not harmonically related. What transmitter performance parameter does a two-tone test analyze? So it's looking at linearity. How linear is your transmitter amplifying signals at different frequencies? Oops, sorry. What is the purpose of a speech processor in a transceiver? This is to increase the apparent loudness of transmitted voice signals. So remember, a good way to think about this with the exam is a speech processor affects the signal that you're generating. There are other processing activities going on in the receiver side, but the speech processing specifically is transmitter related.
Right. So
how does a speech processor affect a single sideband phone signal? It increases the average power of the signal by reducing the high and low peaks. What is the effect of an incorrectly adjusted speech processor? You're going to get distorted speech. You could get excess intermodulation products. I don't think we've covered intermod in this content yet in the 3 nights that we've been going. You can get excessive background noise. So all these choices are correct. What frequency range is occupied by a 3 kilohertz lower sideband signal when the displayed carrier frequency is set to 7.178 megahertz? Since it's lower sideband, you're below the carrier, so you're looking at a signal that goes from 7.175 to 7.178. So if it's lower sideband, you subtract 3 kilohertz. If it's upper sideband, you add 3 kilohertz. And here we go. So here you want to add 3 kilohertz since it's an upper sideband. So the signal will be between 14.347 and 14.350 megahertz. How close to the lower edge of the band's phone segment should your displayed carrier frequency be when using a 3 kilohertz wide LSB? So you want to be above the band edge. So you need to be 3 kilohertz above the edge in this situation. You see the repetitiveness in the questions here. That's a good example. Same question for upper sideband. How close to the upper edge of a band's phone segment should your displayed carrier frequency be when using a 3 kilohertz wide upper sideband? You want to be 3 kilohertz below the edge of the band so that you don't break out of your allowed band. What is the function of electronic keyer? These are so interesting way the book is organized is every once in a while you get these seemingly totally random questions in the middle of a section. This is one of them. I didn't throw it into the miscellaneous catch-all at the end, but I should have. So an electronic keyer just provides automatic generation of the dots and dashes for CW operation. So it basically essentially normalizes the signal length for each dot and each dash. That's probably the best way to think about it. All right, amplifiers. We all use amplifiers. In many cases, they're just built into our transmitters. So mobile radios, have typically a transmitter that can do up to 50 watts. Desktop transceivers typically will go up to about 100 watts. And then there are the external amplifiers. Historically, they've been tube-based. There's a lot of apparently good solid-state amplifiers now as well. But the amplifier goes between your transmitter and your feed line. And what it does is it provides ideally a linear amplification of the signal that's coming out of the transmitter. So RF into the amplifier is increased in power from, let's say, your amplifier set at 50 watts. You've got a 10-to-1 amplifier, so your transmitter puts 50 watts into the amplifier, and the amplifier puts 500 watts into the feed line. That's the basic idea around this. So it's connected between the transceiver and the antenna to boost the signal strength. When receiving, that transmitter is actually switched out of the RF line. So transmit, you go from your transceiver to the amplifier to the feed line. When the transceiver is set to receive, the amplifier is essentially reconfigured so that the feed line bypasses the bypasses the amplifier and runs directly into the receiver. And that is all that magic is handled by what's called a transmit receive changeover relay. It may be a physical relay, it may be an electronic relay, but there is electronic controls within the amplifier that switches the feed line from the amplifier side to the receiver side. Mentioned there's both solid state and vacuum tube amplifiers. The tube amplifiers, if you like fiddling with things and you like using analog equipment, they're a great time because you can spend a lot of time working with them. Essentially what you have to do with the tube amplifier though is when you turn it on, let it warm up, you have to adjust it. And so you have to adjust it so that you minimize the plate current, and you do that using what's called a tune control. And the plate current is the current running to one of the plates on one of the amplifier tubes. And I forgot something. you have to set the band, sorry. So the tube amplifiers are sensitive to the transmit frequency, so you want to set the band. Sometimes you set more than the band on the amplifier. Then you minimize the plate current using the tune control, and that makes it resonant at that transmit frequency. And then you want to adjust the load control to maximize the output power to the extent that you're getting the power output that you want without overdriving the amplifier. And then finally, you go back to the tune control so that you reduce the plate current one more time to bring that maximum output power back down to where you want it. The thing that worked for me for thinking about this when I was doing the exam is you tune for dip, so you want to minimize with tune. You load for peak, so you want to maximize with load, and then you retune for dip. So if you think tune for dip, that's the key component here to remember for any of these test questions. That will help you get the right answer on the exams. And then amplifiers, there's a reference again to automatic level control because you don't want to overdrive your amplifier. If you overdrive your transmitter, the distortion you're introducing into the transmitted RF signal just gets worse as it goes through the amplifier because it's amplified 10 to 1 or 15 to 1 or 5 to 1, whatever your amplifier capability is. So let's talk about the questions that relate to these. So what is the effect on plate current of the correct setting of a vacuum tube RF power amplifier's tune control? This is where tune to dip helps a lot. So you get a pronounced dip as you want to minimize the plate current. Why is the ALC used with an RF power amplifier? Okay, and primarily to assure that you don't excessively drive the amplifier. What is the correct adjustment for the load or coupling control of a vacuum tube power amplifier? So you're going to tune for dip, you're going to load for max. So you want desired power output without exceeding the maximum allowable plate current. What is the purpose of delaying RF output after activating a transmitter's keying line to an external amplifier? This is where that relay comes into play. You want the amplifier to have time to switch. So it needs to switch the antenna between the transceiver and the amplifier output so that you're moving from receiving to transmitting. Same thing when you go back to receiving, is that relay has to kick in again to switch the feed line back to the transceiver. All right, receivers. We've talked about receivers a little bit, but let's go deeper. They essentially amplify and filter all the signals coming from the antenna. So the antenna is not signal or frequency specific. It may have optimizations at certain frequencies. You may have tuned the antenna to be resonant at a particular frequency, but every antenna has a bandwidth associated with it, and it's receiving microvolt and nanovolt signals from around the world all the time. And so the receiver gets all of that stuff, some of which you want and some of which you don't want, as an input signal into the receiver. The receivers have built-in amplification called RF gain. The gain is applied equally to everything that the receiver is receiving. Sorry, within the received bandwidth. Okay, so I should have actually broken this out. When you are using your receiver, you generally set your receiver to receive on a particular band. So that creates a situation in the receiver that says, I'm only interested in signals within this particular bandwidth, from low to high. I'm working in the 20-meter band. Maybe I have, a 100 kilohertz bandwidth as an input filter on that receiver. So everything outside of that is kind of pushed below the noise level, and I'm just looking at 100 kilohertz worth of signal content. The gain will apply to that entire 100 kilohertz of signal. There's a feature called automatic gain control. which will vary the gain automatically so that the output volume of the received signal stays constant for both weak and strong signals. So as you tune across 3 or 4 different signals, if one of them is very weak and you've got AGC running, it'll bring up the volume. As you tune into a stronger signal, it'll bring down the volume so that when you're listening either on a speaker or with headphones, you're not kind of getting blasted at one point, then having something you can't hear at the next point, even though you can see it on the meter. The AGC works by adjusting the voltage that controls an intermediate frequency amplifier in the receive circuitry. And that is measured, that gain, if you will, is measured in S units. S stands for signal. And the S meter is calibrated from S1 to S9. And then there's S9 plus 20, 40, and 60, I believe. So each S unit is essentially a 6 dB change in signal level. And 6 dB, if you remember the math, equates to a 4x increase in signal level. So if you're receiving a 100 microvolt signal, and that's coming in on your receiver at a S3, and you trip across a 400 microvolt signal, that's going to be at an S4. That's the best way to be thinking about it. And then when you hit S9, instead of going to S10, 11, 12, they go S9 plus 20 dB, S9 plus 40 dB. And we'll talk about that a little bit more in a minute. Overload occurs when the received signal is too strong for the circuitry, and you end up with distortion. So you can either filter out the offending signal, or you can reduce the gain using the receive attenuator. Filters are used to both narrow the passband of the signal being received and as a direct side effect to remove an unwanted signal. So you can move filters around over frequency ranges, and you can widen and narrow filters, and you can essentially narrow down to the range of signal that you're most interested in if there's a lot of other stuff going on in that frequency range at the same time. If you're in a quiet area and there's only one signal, you don't have to do anything with filters generally. So notch filters are a particular type, and they're designed to remove very narrow signals. So you can, depending on the capability of your transceiver, you can do notch filters that will do like 100 hertz or 200 hertz or 500 hertz or 1 kilohertz width, and just basically chop things out of your receive band. Passband filter, I mentioned briefly before. Basically, if you're looking at 20 meters and you want to only look at 100 kilohertz component of that, you use a passband filter to basically cut everything off outside of that 100 kilohertz range. There's a trick with CW. If you're listening to CW and there's a lot of interference, sometimes you can switch the sideband. So you switch from upper to lower sideband, and that essentially moves the filter that you're using. And sometimes that will have a positive effect of eliminating an interfering signal. So that's a trick that the CW operators use, to basically reverse the sideband to move the filter above or below the displayed carrier frequency so that you can chop something out that you don't want to be hearing. A noise blanker is designed to essentially quickly reduce the gain and basically take a sharp pulse out of the received signal stream. So they affect everything in the band, but they will take millisecond pulses or 10 millisecond pulses out of this receive band if you need that to be happening. And then finally, there are noise reduction capabilities that are mostly handled by digital signal processing. As you increase your noise reduction, you're basically taking signal out of the receive stream, and you may actually lose the stuff that you're interested in. So the bottom line with noise reduction is that it can increase distortion of the received signal. So let's do some questions. What is the purpose of the notch filter found on many HF transceivers? It reduces interference from carriers in the received passband. What is the benefit of using the opposite or reverse sideband when receiving CW? May be possible to reduce or eliminate interference from other signals. How does a noise blanker work? Reduces the receiver gain during a noise pulse for a very short period of time, typically in the order of milliseconds. What happens as a receiver's noise reduction control level is increased? The received signal may become distorted. Which of the following is a common use of a dual VFO feature on a transceiver? Okay, we haven't talked about this at all. Many transceivers can operate in split mode, is one way it's called, or have two VFOs, and you can essentially tune one for transmit and tune the other one for receive. So it allows you to transmit on one frequency and while you're listening on a different frequency. This particularly comes into play if you're doing HF contesting. Lots of people seeking QSOs in contesting will transmit on one frequency, listen on another. They'll tell you that when they're announcing themselves, and it basically allows them to hear you without having lots of people interfering all at one time on one frequency. What is the purpose of using a receive attenuator? Is to prevent receiver overload from strong incoming signals. What does the S meter measure? It measures the received signal strength. How does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter? Well, the math, what does 20 dB equate to? Well, 20 dB equates to 100x. So S9 plus 20 dB means you're getting a signal that's 100 times more powerful than the signal at S9. How much change in signal strength is typically represented by one S unit? That's 6 dB, four times signal increase. How much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? Well, you want a 6 dB change on the receiver, so you need a 4x increase in transmit power. Okay, HF station installation. There's a lot of stuff in this section, so I've broken it down a little bit more granular. We'll talk first about mobile HF. You know, many of us do mobile VHF. Not so many people do mobile HF. Everything that's here actually applies to both VHF and HF, interestingly. So, you know, a typical mobile radio, VHF mobile will transmit up to 50 watts. HF mobiles, some of them will transmit up to 100 watts. So you're going to be drawing 15 to 20 amps at 12 volts in your car when you're running one of those radios transmitting. So you want that radio wired directly to the battery. And you want it wired with probably number 10 or perhaps number 8 stranded copper wire. And you want fuses in both the hot and neutral leads, just for total safety. Mobile antennas are electrically short and less efficient. As frequencies go down into HF bands, the electrically short antennas become even less efficient. And there's an example that we'll get to in a minute here about why that might apply. And then the best way to think about a modern automobile is that everything interferes with the radio. There are probably systems in the car that don't, but the computers, the fuel pump, the windows, the battery charging, everything gets in the way of the radio. They all generate RF, and radios are great at picking up RF, especially if it's right there. Um, all right, another section, grounding and bonding. If you are running HF in your station at home, in the shack, you want all of your equipment bonded to a common bus. And you want that because you want to avoid the possibility of getting RF on the chassis and getting an electrical burn from that RF. So the recommended method is to have like a common bus. I actually use a 1/2-inch copper pipe, and I use a short copper strap running from each piece of equipment to that copper pipe. You can use number 10 or 12 copper wire as well. You want to keep those runs as short as is possible. You want that bus grounded to the AC house ground. Again, you want to keep the connection short. In an ideal world, you'd actually ground it to a ground rod, keeping the connection short here as well. That's always trickier. There is a risk that if you have a long connection to ground, that it could be resonant at an odd number of quarter wavelengths at any frequency. And if that occurs, then you get a high impedance in the ground path, and you get RF on the chassis, and you're at risk again of getting an RF burn. And finally, you want to avoid ground loops, so don't run wires in a circle around your equipment. Run wires to a common bus. Run that bus to AC ground. And then I'll put in a little pitch here. The ARRL actually has an amazing grounding book, which is many, many, many. I think it's like 150 or 200 pages. Well worth reading. Very interesting and very thought-provoking, frankly. And then finally, the other topic here is RF interference. So we are transmitting, and when we transmit, we're generating RF, and that RF may be picked up by the TVs or the thermostat or the oven or the coffee maker or et cetera, et cetera, et cetera. Nominally, all of that equipment is sold certified for FCC part, I think it's 15. It says it's not, it's safe from RF interference, but many places just declare that that's the case and don't actually test for it. So what you might hear, if you are transmitting on CW or FM or using a data mode, the interference is typically going to be a buzz or a hum or a click or a thump in a particular piece of electronic equipment in your house when you're transmitting. If you're transmitting SSB, obviously it's voice, and you're going to hear some kind of distorted or garbled voice or sounds in the equipment. So let's talk about the questions. Which of the following might be useful in reducing RF interference to audio frequency circuits? You can put a bypass capacitor in place on the equipment from the signal to ground, and that will take high frequency signals out of the signal line. Which of the following could be a cause of interference covering a wide range of frequencies? So the correct answer is arcing at a poor electrical connection. Essentially, you want something that's spewing noise. And so an arc is a multi-frequency signal that's just going to generate a lot of crap, frankly. What sound is heard from an audio device experiencing RF interference from a single sideband phone transmitter? We did talk about that. Distorted speech will be what you'll typically hear. What sound is heard from an audio device experiencing RF interference from a CW transmitter? You're going to get on and off humming or clicking. What is a possible cause of high voltages that produce RF burns? This is where the ground wire could have a high impedance on that particular frequency. What is a possible effect of a resonant ground connection? Same thing. High RF voltages on the enclosures of station equipment. Why should soldered connections not be used in lightning protection ground connections? This is another one of those. Why is this question in this section? The bottom line is if you have a soldered connection that gets hit by lightning, that solder is just going to evaporate. So you don't want a solder joint. And if you look at tower construction methods and tower grounding methods, there's some really good examples in the literature about that and about how you actually want to ground that tower. There's no solder anywhere in sight. There are some very interesting ways of doing it. Which of the following would reduce RF interference caused by common mode current on an audio cable? Well, you want to basically slurp that common mode current out of the cable so it doesn't get into your radio, if you will. So you put a ferrite choke on the cable. Maybe you put several on the cable. It just depends. So a good place to start is with one. Sometimes it takes several. Sometimes you actually have to wrap the cable through a coil, through a choke. May take 6 or 8 or 10 wraps sometimes. So there's a lot of experimentation. I think there's actually a lot of science supporting it too, but everything that I've done, everything I've read basically says experiment until you get the outcome that you're seeking. How can the effects of ground loops be minimized? And this is where you bond your equipment enclosures together. Take them all to a common bus. What could be a symptom caused by a ground loop in your station's audio connections? So ground loop typically introduces hum into your transmitted signal. So you'll receive a report of hum on your transmitted signal when you're talking to other people. What technique helps to minimize RF hotspots in an amateur station? Again, bonding all the equipment enclosures together. Why must all metal enclosures of station equipment be grounded? Ensures that you cannot get hazardous voltages on the chassis. Totally about safety here. Which of the following direct fuse connections would be best for a 100-watt HF mobile installation? Okay, go to the battery with heavy gauge wire. Why should DC power for a 100-watt HF transceiver not be supplied by the vehicle's auxiliary power socket? The answer is very nicely done. Sockets wiring may be inadequate for the current drawn by the transceiver. If you actually try this, I would do it on not a car that you like a lot because you're going to melt all the wires behind that socket. It's going to be pretty ugly. Which of the following most limits an HF mobile installation? This is the issue of the efficiency of an electrically short antenna. Which of the following may cause receive interference to an HF transceiver installed in the vehicle? All of the choices are correct. Battery, fuel, and control computers. So let's talk more about HF antennas. Most mobile antennas are vertical whips. At HF frequencies, a full-size quarter wavelength whip would start at about 10 feet if you're at 24 megahertz or a higher frequency. If you're going lower in frequency, then you're quickly going beyond the 10-foot length. And it's just not feasible to be driving around with that kind of an antenna. Antenna loading techniques are used to increase the electrical length without increasing the physical length. And you can load an antenna with either a coil, and they're typically installed at the bottom or in the center, midpoint of the antenna, or you can load the antenna with a capacitance hat, which is installed at the top of the antenna. Loading the antenna reduces the efficiency of it, narrowing the operating bandwidth of the antenna. There's a measurement called Q, or the quality factor, which shows you the correlation between bandwidth, frequency, and efficiency. You don't get into that in the general exam, though, so don't worry about it. I shouldn't have brought it up. There's a particular type of antenna called the screwdriver antenna, which has a loading coil at the base and a whip above. And the tap on the loading coil is adjustable. So that's why it's called a screwdriver antenna. That tap can move up and down. And so you can set the tap for a particular frequency. And you can basically then, as you learn your antenna, you can figure out what the settings need to be for different frequencies to get the best transmit efficiency at that frequency. And then most mobile whip antennas also include what's called a corona ball at the tip to eliminate high voltage discharges when transmitting. So the antenna can, since you're putting, like, say, 50 or 100 watts out the transmitter, you can build up a static charge on it. And the corona ball will ensure that that stays discharged, and so that if you touch the antenna or somebody else touches the antenna while you're transmitting, they don't get shocked. All right, circling into the end here. What is the purpose of a capacitance hat on a mobile antenna? To electrically lengthen a physically short antenna. What is the purpose of a corona ball on an HF mobile antenna? To reduce the RF voltage discharge from the antenna while transmitting. What is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna? The operating bandwidth may be very limited. And we have two miscellaneous questions. Fun ones. So what is the purpose of an antenna tuner? Well, what is an antenna tuner? An antenna tuner is a piece of instrumentation that you put between the transmitter and the feed line. And I think all modern solid-state transceivers now come with a built-in antenna tuner. They can typically handle standing wave ratio difference of up to 3:1, and you can tune the transmitter within the transceiver to accommodate that kind of standing wave ratio. If you have an antenna that's got a higher SWR on it, then you need a separate antenna tuner, most of which can handle up to a 10:1 standing wave ratio. And the basic idea is that the antenna tuner enables you to optimize the amount of power that gets to the antenna. It doesn't change the SWR in the feed line, but it brings the transmitter into happiness with the feed line. That's how I like to think about it. So it's going to essentially increase the power transfer from the transmitter to the feed line. That's the essential nature of an antenna tuner. Most transceivers, as I said, HF transceivers have antenna tuners built in to handle up to a 3:1 standing wave ratio. And that's it. I wanted to throw one additional resource out that hasn't been talked about in the last two classes. It's called hamexam.org. It's a great site if you want to do practice exams. They also have this thing they call flashcards. You can basically start a flashcard sequence, and it will ask you random questions across the spectrum of the general test, and keep stats for you, and so you can see what you're getting right, what you're not getting right, need to go study more for.
Welcome to week 3 of the General Class License Training. I'm Tim Hanna, WB9NJS, got licensed as WN9NJS in 1973, so been at this a while. And remember, folks, this is these presentations are really the culmination of work from several folks involved in several of the inland amateur radio organizations, MAX, Mendocino Auxiliary Communication Service, the Mendocino County Amateur Radio Communication Service, McCarks, and the Willis Amateur Radio Society. Many of us giving this presentation are members of one or all of those, and basically it's your local ham community that's doing this for you. Okay, for tonight, again, we're covering, as you can see, Peter covered quite a bit in G4. There's 5 questions on the test, 60 questions in the pool, a lot of material. Then we've got a little bit less here on signals and emissions. There's 3 questions on the exams and 43 questions in the question pool. let's talk about what some of those topics are in the signals and emissions. Um, there's carrier modulation, AM, FM, single sideband, modulation envelope, digital modulation, overmodulation, link budgets and link margins. Oh, frequency changing, bandwidth to different modes, deviation, intermod, that's a fun one. And a section on digital emission modes. And one question will, from each of these three categories, will appear on the exam. Things are kind of scattered about in the ARRL book as well. In the notes that I publish, you'll find information in Chapter 3, parts of Chapter 5, lots of Chapter 5, parts of Chapter 6. So the pages are called out in the first page of my notes document. So before we go into that, let's take a quick review down memory lane. Let's hope your memory is still working. We've been through several sections already, so I pulled a few questions from each of those sections to see what you remember. So which of these classes of amplifiers has the highest efficiency? What's an efficient amplifier? Well, it's a Class C amplifier. It's not a very linear amplifier. It may distort the output versus the input, but from an electrical efficiency, it's the highest. Which of the following describes a type N connector? An N connector is a coaxial cable connector. It's a moisture-resistant RF connector, and it's useful up to 10 gigahertz. Actually, if you look inside the male N connector, you'll see there's a rubber gasket in there, and that's what helps it be moisture-resistant. Oh boy, what happens when you put a 21 millihenry inductor in series with a 50 millihenry inductor? Well, this is the easy one, folks. When you put resistors or inductors in series, all you have to do is add. So the answer is 70 millihenries when in series. Oh, how does the higher sunspot number affect HF, high frequency propagation? Well, we're coming up on the peak of the 11-year sunspot cycle, so we're about to find out as sunspot numbers rise. This generally indicates a greater probability of good propagation at higher frequencies. 10, 12 meter, 15 meter bands are starting to open more frequently. Notice this is a couched answer. Generally indicates a greater probability, so there's no guarantee that you'll have a favorable effect from higher sunspot number. Okay, get to antennas. How does the feed point impedance of a horizontal half-wave dipole antenna change as the antenna height is reduced to 1/10 of a wavelength above the ground? Steve had a very nice graphic on this last week, and it showed that as you lower that antenna, as you get that half-wave dipole closer to the ground, that feed point impedance steadily decreases. This kind of ties into one of the topics Peter just mentioned. If the SWR on an antenna feed line is 5:1, and a matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what's the resulting SWR on the feed line? Well, that matching network is just there to make the transmitter happy, to think that there's a perfect match that it's feeding. But as far as what happens on the coax, absolutely nothing. The SWR on the coax is still 5:1. Okay, why are HF scatter signals in the skip zone usually weak? Well, if you remember, scatter is a mode that covers the skip zone, usually the parts that hopped over geographically. But the reason is that only a small part of the signal energy is actually scattered. Most of it's going up into the ionosphere and hopefully getting bent back down. So let's get into some of the basics. Kind of going back to some of the technician material. There's several type of emissions that can come from your station. And actually the universe is full of electromagnetic radiation, including RF, and most of it's random from just a variety of cosmic sources. The energy simply exists, and it doesn't really carry any information, and unless we find ET out there. But in order to use RF to communicate, information must be added or extracted to the radio signal. So what happens during radio communications? Well, from the transmitting side, the information, whether it's voice, data, video, commands, any information that you want to transmit, is converted to an electronic form. The information in electronic form is added to a radio wave somehow, and the radio wave carrying the information radiates from the station antenna. So you're actually transmitting a radio wave with that information encoded. On the receiving end, what happens? Well, a radio wave carrying the information is intercepted by the receiving antenna. Receiver extracts the information from that received wave, and then it's converted to a format that can be understood, whether it's sound, image, characters, words, or a response to a command. So that act of adding information to a radio wave or a carrier is the process known as modulation. And one of the simplest ways to modulate a carrier is simply to turn it on and off. You create a Morse code or a CW signal. But it's also possible to encode speech or music, out on the amateur bands for the music, or to encode digital data in the signal. Different modulation techniques alter different properties of the wave in order to add that information. You can alter the amplitude of the signal. We'll get into this in a bit. Or you can alter the frequency or the phase of the RF signal. Let's talk about these three common ways to add voice information to an RF carrier. Okay, this is right. By the way, the presentation is set up so the text that you see in italics is generally taken from the question in the question pool. Excuse me. So, amplitude modulation, AM. How does that modulate the signal? It varies the instantaneous power level. Amplitude, instantaneous power. Frequency modulation, FM, changes the instantaneous frequency. So that's how to find the right answers. Phase modulation, or PM, changes the phase angle of an RF signal. So those are the concepts in the questions. None other question about phase modulation, and it may be produced by a reactance modulator connected to the transmitter RF amplifier stage. So if you change the reactance in the transmitter amplifier stage, you can shift the phase around, and that's what a reactance modulator does. Bandwidth. Let's talk about bandwidth. Different types of modulation and information produce different signal bandwidths. In the question pool, in this regard, the one question is single sideband SSB is a type of amplitude modulation, produces phone emissions using narrower bandwidth than FM or PM. That's the key. Single sideband, narrower bandwidth than FM or PM. Okay, one of the concepts that comes up is the modulation envelope of an AM signal, and that's defined as the waveform created by connecting the peak values of the modulated signal. What does that mean? So if you look at a signal that's being modulated, the amplitude is being modulated, the signal over time will go up and it'll peak and it'll come back down, and following the waveform of the modulating signal. And if you go at microsecond intervals and you make a dot and you connect those dots, you'll trace an outline, and that is the waveform, and it's created by connecting the peak values of the modulated signal. Peter touched on this. Overmodulation. We want to add information effectively to the signal. We want to modulate it properly. Overmodulation, however, is not a good thing. as Peter mentioned, it can cause excessive bandwidth. Instead of staying in that um, 3 kilohertz window for good amateur practice for a sideband signal, you might extend over um, and result in what can be called splatter, where your signal extends out on adjacent frequencies. Overmodulation, it can cause what's known as flat topping of an amplitude modulated phone signal, and that results in signal distortion caused by that excessive drive or speech levels. So yeah, overmodulation, not a good thing. It's not good for other people trying to use the band, and your signal usually sounds pretty poor as a result. Okay, we're going to shift gears here, and we're going to start talking about digital modes and digital modulation modes. And we're going to start with really one of the older modes. You'll see here on the screen RTTY, pronounced RTTY. It stands for radio teletype, and this has been around for almost 100 years. I believe the Baudot code, which it uses, which is a 5-bit code, was developed in the 1930s. And if you're quick with your math, since it's a binary system, you got 5 bits, so you have 2 to the 5th combinations. Well, that's only 32 unique characters. And if you've got 26 in an alphabet, you've got numbers, you've got punctuation. How do you do it? Well, one thing is all of the letters are sent as uppercase, but really old technology. It's a Baudot code, 5-bit code with start and stop bits. Most commonly, RTTY signals are produced by frequency shift keying, or FSK, of an RF signal. And this is right out of the question pool. And I'll explain what it means. Direct binary FSK modulation is generated by changing an oscillator frequency directly with a digital control signal. So you have your transmitter oscillator running at a certain frequency, and now you apply a signal to that then shifts that frequency. It doesn't shift it back and forth in between it. It shifts a discrete amount. And those two separate frequencies of the FSK signal are known as the mark and the space frequencies. So when that digital control signal is in one condition, a 1, 0, or a high, low, whatever you want to call it, the transmitter will be on the mark frequency. When it shifts to the other state, now the transmit frequency will shift to the space frequency. So that's the mark and space designation of FSK signals. One of the things about RTTY, really, it lacks the error detection and correction modes that are available in some of the more modern digital modes. So let's talk about those. Digital mode error correction. Well, one of the sets of questions you'll find relates to automatic repeat request, or ARQ. So what is ARQ? Well, it's a system where when you're transmitting data, the receiving station checks the integrity of the data that it received. Does this make sense? If it's good, it sends an ACK, acknowledge, hey, that's good, send me another one. If it doesn't get the packet right, doesn't get the message right, it sends an NAK, or a not acknowledged. And that's a request for the transmitting station to repeat. So the receiving station checks. If it's good, send an ACK. If it's not, you'll send a NAK, NAK. Hey, repeat that. I didn't get it. So what happens if you fail to exchange information too many times on too many NACs? So you're always, the receiving station is always asking, hey, what was that? Tell me again. Tell me again. That continues too long, it'll result in a dropped connection. So if you're using ARQ, you'll fail to exchange information. Failure to exchange information will result in a dropped connection. Okay, you might notice that there's a kind of a flaw in ARQ. It can really slow things down. If the transmitting station, if the signal's weak and the receiving station keeps repeating, say, hey, send that again, it can slow it down. So an alternative to that is forward error correction, or FEC. What's forward error correction? Well, the receiver detects and corrects errors automatically. And how does it do that? That's accomplished by transmitting redundant information in the outgoing message. So there's parts of the message that are duplicated. So if the receiving station isn't sure, it can check correct automatically, and that would be forward error correction. Most of these digital modes tend to use a packet structure for transmission. The data that you want to send is packaged in a structured format, and the basic format is there's a header, and then there's a payload, which is actually the data that you want to send, and then there's a trailer. So those are the three segments of a packet structure. And the question in the question pool is, what does that header contain? Well, the header in the packet contains the routing and handling information, which makes sense. That's the first thing you're going to want to send when you're sending information. Hey, this goes to so and so, and here's how to get it there. Okay. There are tons of digital modes, and it seems like there's more just about every day, and some of them are pretty neat. Let's dive into one that I really don't have any experience with, and it's WSPR. And that mode is used as a low power beacon for assessing HF propagation right out of the question pool. Another mode that has a couple questions is QPSK31. Okay, well, FSK is frequency shift keying. What do you think PSK is? Well, that's a phase shift keying. And a PSK31 uses a 0, 90, 180, and 250-degree phase shift modulation. That's where the QPSK comes from. Other characteristics of that type of signal, it is sideband sensitive. You have to be operating on the correct sideband. The way it's built, the encoding provides error correction, that forward error correction. And the bandwidth is approximately equal to BPSK31. And the actual answer for the question on this test is all of the above. All three of those appear in the answer for this question regarding those characteristics. Okay, we'll throw in another quick note. There's two questions on PSK31, again, a phase shift keying. Varicode is the term for the code that's used for sending characters. Varicode is PSK31. And when you use PSK31 and transmit uppercase characters, it uses a longer varicode, so it actually slows down the transmission. PSK31 varicode, uppercase letters use longer varicode, and it slows things down. Okay, this is a really neat one just because of what it can do. FT8. What the heck is FT8? Well, it's an increasingly popular narrow band digital mode. That's the word you'll see in the question. And how do you make FT8? Well, the fact that it's an F in the designation means it's probably frequency shift keying, and the fact that there's an 8 means that there's 8 tones used. So FT8 uses 8-tone frequency shift keying. That's the answer. Neat thing about FT8, it can receive signals with very low signal to noise ratios. What does that mean? You can actually transmit and receive information using FT8 on signals that you can barely hear with your ear listening to the receiver. So it can receive signals with very low signal to noise ratios. That means the signal isn't much above the noise floor. Okay, and when an FT8 signal is reported with a +3, so an FT signal report +3, it means that the signal to noise ratio is +3 dB and a 25 kilohertz bandwidth. That's right out of the question. What does that mean? Well, +3, that's you're only 3 dB above the noise across the bandwidth. That's not a lot. I mean, most voice signals are probably 20 to 30 dB above the noise. So this is a signal that would be way down there, almost difficult to hear with the human ear. Okay, a couple of questions thrown in about link terminology. Um, One is link budget. What's the link budget? Well, it equals the transmit power plus the antenna gain on either end of the link, both the transmit and receiving gain, minus the system losses. So you'll have some path loss between the two locations. So you take the transmit power, you add the antenna gain, you subtract the system loss. That's your link budget. That tells you how much power, how much signal you would expect to have at the receiver. And you would like to have a robust link budget. And the other concept is the link margin. Well, what is that? That's the difference between the receiver power level and the minimum required signal at the receiver. So, what kind of power are you actually getting at the receive terminals versus how much do you need to actually get a usable signal? So, if you have a strong link margin, you'd be well above the minimum that the receiver needs to function and give you some intelligent information. Okay, let's jump into a few of the questions on this part. What's the modulation envelope of an AM signal? Well, we talked about that. That's a waveform, and it's the waveform created by connecting the peak values of the modulated signal. I left out an L there. Sorry about that. Next question. Which of the following is an effective overmodulation? We know it's something that you don't want. Well, it's not insufficient audio. You probably have too much. It's not insufficient bandwidth, and it has nothing to do with frequency stability. It's excessive bandwidth. You don't want to overmodulate. Your signal splatters. It goes beyond a reasonable range, and it causes problems and distorts your signal. What type of modulation is used by FP8? Well, let's look at the designation. F would be a frequency shift keying. 8 is probably the tones. And that is indeed the right answer, 8-tone frequency shift keying. So FT8 is shifting that transmitter not between just 2 tones, a mark and a space, but between 8 different frequencies. What action results from the failure to exchange information due to excessive transmission attempts when using an ARQ mode? Well, ARQ uses the ACK and the NAC. Acknowledge, send me another, not acknowledge, send it again. So if that happens too many times, that connection will be dropped. And which of the following describes the Baudot code? That's the one that was developed for radio teletype. Well, it's an older code, so it's only a 5-bit code, and it uses additional start and stop bits. And that goes back to the days of mechanical teletype machines. And back in the day, I owned one and used it for radio teletype on the ham bands. So not a good way to make your wife happy with a machine in the next bedroom that's clanking and cluttering away. Anyhow, enough of that. Let's talk about hams and Wi-Fi. Wi-Fi is all around us, but did you know that amateurs actually share channels on the unlicensed Wi-Fi 2.4 gigahertz Wi-Fi band? Yeah, and that is actually kind of neat because that allows some hams to use commercially available Wi-Fi equipment to build mesh networks. Those are data networks. And what's the neat thing about mesh networks? Well, the mesh network microwave nodes, which would be these Wi-Fi devices, can provide a robust network. And what that means is if one node fails, the packet may still reach its target destination via an alternate route. That's what a mesh network means. There's multiple routes to get the data from point A to point B. Okay, there's a series of questions on a digital tuning aid. And the most common that you're going to find and the questions that revolve around is the waterfall display. So what's a waterfall display? What does it look like? Well, it looks something like this. The top section here, you see these streaks. That's a dynamic section. It's moving down continuously with the most recent data at the top and then it falls down just like water over a waterfall. And that's the down axis. The bottom axis, we look here, we're actually looking at um, frequency. So going from left to right here along this bottom axis, you're looking at a range of frequencies, and I can't quite read this, but this is spanning a range of frequencies, much like a spectrum analyzer shows signals on a range of frequencies. So the time is vertical, like I mentioned, going from the top to the bottom of a waterfall. The most recent reading or data is at the top, and the oldest works its way to the bottom before it falls off. And the signal strength is the intensity. That's how it's referred to in the question. Horizontal frequency is horizontal, time is vertical, signal strength is intensity. In this case, it's color, and you'll notice that different colors in streaks here. You'll notice the more close it approaches red is the higher signal. The cool blues are down here. So this area here where you see kind of an orangish red streak, you'll notice it also corresponds with a peak in the signal displayed down here. There's a peak here. Same thing here. There's a peak in the RF spectrum, and there's a corresponding stripe with it. And one more question about waterfall display. If you see one or more vertical lines on either side of the data mode or RTTY signal, or the one that you want to see, and on either side of it, there's a solid vertical line, that's an indication that the signal is being overmodulated. So one or more vertical lines on either side, overmodulation. Okay, so far when we've been talking about digital modes, mostly it's been data transmissions. It's text, it's characters, it's whatever. But voice can also be digitized in many common systems. We use this every day. Probably many folks' telephone system is a voice over IP. That's a digital system for internet. For hams, there are three common modes, and it kind of depends on the manufacturer. There's DMR, digital mobile radio, D-Star, which I believe is an ICOM protocol, and System Fusion, which is a Yaesu protocol. I think I got that right. It doesn't matter. That's not part of the question. But just to let you know, there is actually a System Fusion repeater here in Willits, the 14513 machine on Laughlin is System Fusion, and it can be switched between a digital and analog mode. Most of the time it's operating in analog mode, but if somebody has a System Fusion radio and they want to go digital, they can switch the repeater to that mode and talk to someone else that's using a digital transceiver. For those of us who are still listening on an analog receiver, you won't hear anything but what sounds like a rush of noise. The audio has been digitized and sent that way on any of those three, but locally it would be on the System Fusion. Digital mode bandwidth. Every mode has a characteristic bandwidth. One of the important concepts, and this is in the question, and you'll find it later in week 5, there is a relationship between the transmitted symbol rate and the bandwidth. The higher symbol rate requires wider bandwidth. Okay, this is the basic concept. The faster you try to send information, the wider bandwidth is required. So higher symbol rates require more bandwidth. This is why the character rate, or what's known as the baud rate, is limited on the HF bands. And I know Barbara will get into that in week 5. So one of the other concepts of digital, not just digital bandwidth, but any bandwidth, and this overlaps with what Peter talked about, is the bandwidth. And what you want to do is you want to match your receiving bandwidth to the bandwidth of the operating mode, and that's going to result in the best signal to noise ratio. Matching received bandwidth, the bandwidth of the operating mode, best signal to noise ratio. So If you want to operate CW, Morse code, it's a narrow bandwidth mode. So you'd want the receiver to a narrow receive bandwidth in order to optimize the signal to noise ratio. If you're operating single sideband phone, you'd want to make sure that that receive bandwidth was in that 3 kilohertz range in order to have the best signal to noise ratio. So there are two questions about bandwidth and deviation on the test. And I'm not going to try to get in here and explain it. It's not that complicated, but I'm going to just give you the questions and the correct answer. So G8B06, total bandwidth of an FM phone transmission having 5 kilohertz deviation and 3 kilohertz modulating frequency. The answer is 16. So 5 kilohertz and 3 kilohertz. Look for an answer of 16 kilohertz. G8B007, the frequency deviation from a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation, 152 megahertz FM phone transmitter. It's really not that hard to calculate, but I think it's easier to remember if you're seeing a question about 146.52 FM phone transmitter, that it's 416.7 hertz. And if you really want to dig into it, look at pages 510 and 511 in the book. Okay. The concept of duty cycle comes up, and it is important with digital modes because some modes actually use a high duty cycle. That means you're pushing the transmitter at near its power rating for extended periods, where with voice, the peaks go up and down. With a digital signal, it can be a high duty cycle where you're really working it. And it's important to know the duty cycle of the mode that you're using when you're transmitting. That's from the question. Because modes with high duty cycles could exceed the transmitter's average power rating. That's the question. Why is it important to know? Because modes with high duty cycles could exceed the transmitter power rating. How would you compensate for this? Well, it's not in the question pool, but if you were faced with this, the way to compensate for it is to limit the transmit time or reduce the transmit output power, and that'll help you avoid overheating the transmitter. Okay, which of the following provide digital voice modes? Whisper, no, that was Easy Pal. No, I don't recognize any of those except the last one. DMR, D-Star, and System Fusion. Those are digital voice modes. Which of the following describes a waterfall display? That's a tuning aid for digital signals. And if you remember the graph that I showed you, excuse me, frequency along the bottom axis is horizontal. The signal strength is the intensity or the color, and the time is vertical, with the most recent piece of data at the top of the display, and it works its way down as it follows a waterfall. What's the relationship between the transmitted symbol rate and the bandwidth? Well, there is a very clear relationship. Higher symbol rates require wider bandwidth. The faster you try to send data, the more bandwidth you need to accomplish it. Why is it important to know the duty cycle rating of the mode you're using when you're transmitting? Well, if you're not careful, some of those high duty cycle modes could exceed the transmitter's average power rating. You overheat the transmitter, overwork it. So you need to know, it's important to know the duty cycle of the mode you're using. And we touched on the fact that hams actually have access to some Wi-Fi bands as shared users. So what is true of a mesh network microwave nodes? What can they do? Well, what's true is if one node fails, the packet, the piece of information, may still reach its target station via an alternate route rather than being linear point to point. It's multiple points to multiple points. So there's lots of ways to get that packet through if one node fails. Okay, coming into not quite the home stretch here, but we're going to go over a little review of practical circuits. Mike covered this in week 1. One of the things he talked about are oscillators, and oscillators create signals at a desired frequency. Other circuits are mixers or multipliers, and they transform the frequency from an oscillator to different frequencies. So that's what a mixer or multiplier does. What's a mixer? Well, if you combine frequencies from two oscillators in a mixer, that's a process known as heterodyning. Yeah, combining frequencies in a mixer, term for it is heterodyning. So what happens when you mix two signals in a mixer? Two RF signals, you have two inputs to a mixer, you've got one output. What happens? Well, by combining the combination of the mixer's local oscillator, abbreviated as LO, and the RF input frequencies at the output is equal to the sum and difference of the two input frequencies. So the combination that you get of the two signals coming into a mixer appear at the output as the sum and the difference of the two frequencies. What does this mean? Well, here's an example. If you mix a 5 megahertz signal with a 21 megahertz signal, the output of the mixer has two signals, one at 16 megahertz, that's 21 minus 5, and one at 26 megahertz, 21 plus 5. So the output of a mixer has the sum and difference of the two input frequencies, the one from the local oscillator and the RF input. Mixers and multipliers, they can actually do some pretty neat things. Out of the question pool, you can use a local oscillator to produce an output at an intermediate frequency. So one of those outputs that you're getting from the mixer, you want to use as an intermediate frequency. And in the question, it says the local oscillator or the LO input may be varied or tuned to convert signals to an intermediate frequency or an IF. So a local oscillator can be varied or tuned, and it converts the other signal into an intermediate frequency. Sometimes interference occurs, and interference that occurs from a signal that's 2 times the desired intermediate frequency or IF. That's known as image response. So interference at 2 times the desired IF is image response. That's in the question. Frequency multiplier. What does that do? It transforms the input frequency to an output frequency at a harmonic or an integer multiple of an input. So in the question pool, it asks what stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency, and that would be a frequency multiplier. The example I show here is in that VHF radio, you may be working at a lower frequency of 49 megahertz. You run it through a 3 times frequency multiplier, and you wind up at 147 megahertz, which is in the VHF FM portion of the band. So if you take the harmonic of a lower frequency and you raise it to a desired operating frequency, you're using a frequency multiplier. Well, excuse me, mixing and multiplying is pretty neat. Unwanted mixing and multiplying really isn't. Unintentional mixing of signals creates what's known as intermodulation, and I believe Peter touched on that. So the definition that you'll see in the question, the process that combines or mixes two signals in a non-linear circuit is intermodulation. It produces unwanted spurious outputs, known as intermodulation. So a process that combines two signals in a non-linear circuit that can produce unwanted spurious outputs. Intermodulation. What does that mean? Well, the two signals can combine. This is an example, it's a very common example. In a bad electrical connection, which happens to be a non-linear circuit, And that can produce interference, also known as intermod, and also known as a potential terrible headache, not physically speaking, but um, the unwanted mixing of RF signals can cause all kinds of interference that you're chasing around trying to fix. Um, that's not too bad, maybe in your home ham station, but you get up at a commercial radio site where many amateur radio repeaters are located, say over on Matheson Peak. There is all kinds of RF in that environment from various transmitters on various frequencies. So you can get unexpected mixing that produces intermod. So there's two other questions to pool relating to intermodulation products. Um, Unfortunately, I couldn't find a good explanation in the ARRL book explaining why these are the right answers. So I'm just going to give you the question and the correct answer and suggest that you memorize it. G8B05, which of the following is an odd order intermodulation product of frequencies F1 and F2? Well, it's 2 times F1 minus F2. That's an odd order intermodulation product. I did not see the definition. The other question is, which intermodulation products are closest to the original signal frequencies? Well, it's the odd order that we just talked about. Again, I failed to find anything explaining why those are the answers. Maybe you'll have better luck than I do. Okay, we're into our last round of questions here. We should have a few minutes at the end to see if there's any other. But so from this last group, what process combines two signals in a nonlinear circuit to produce unwanted spurious outputs? Well, it's a form of mixing that we call intermodulation or intermod. Which intermodulation products are closest to the original signal frequencies? Well, we just talked about that. I'm not sure why, but it is the odd order intermodulation products that are closest to the original frequencies. What's another term for mixing of two RF signals? You put them together, and what happens? Well, the term is heterodyning. That's a fairly old term. You might see some older receivers, referred to as a super heterodyne receiver. That means there's multiple mixing going on as the received signal is processed. Heterodyning, term for mixing two RF signals. And which mixer input is varied or tuned to convert signals of a different frequency to an intermediate or an IF, intermediate frequency IF? Well, the input that you're going to vary or tune is the local oscillator. That's the one you have control over. So that's the input that's varied or tuned, local oscillator. What combination of a mixer's local oscillator, LO, and RF input frequency is found at the output? So what combination of the inputs appear on the output of a mixer? Well, that's a simple one. It's the sum and the difference. I showed you a 21 megahertz mixed with a 5 will give you a 16 and a 26 megahertz signal on the output. So it's the sum and difference of the two inputs. And that's it.